Welcome back, Calculus 2 students. We're going to continue with our parametric equations discussion, only now we're going to get into calculus with parametric equations, which hopefully everyone's been waiting for because we are in fact in a calculus class. We ought to be doing some calculus. As a motivating example, I want to return to our parametric equations for a line in which we found that the line passed through the point 3,7 and had slope -5/2. And later on we had an example where the t's were replaced with cosine t, and the line still had a slope of -5/2. So even though this was not the entire line, it was only a segment, even though we had oscillation back and forth with these points, the dy dx, the slope of the line, was in fact -5/2. And that should make a little bit of sense that we've got a rate of change for y with respect to t that is 5 times that of x. And so that suggests that the dy dt, how fast y is changing with respect to t, and how fast x is changing with respect to t, ought to determine the slope of the line, the how fast y is changing with respect to x. In fact, we've already known that all along since Calculus 1 because it's something called chain rule. So if we were to compute dy dt, by chain rule we could actually compute dy dx times dx dt. If we want to solve for dy dx, we have dy dt over dx dt. And so if we want to find dy dx, we merely have to solve for dy dt and dx dt, and once we compute those, we'll take the quotient and compute the answer. So let's see how that works with this example where we have the cosines. So dx dt, take the derivative of 3, that's 0, we have a -2, and then we have the derivative cosine, which is negative sine. And so 2 sine t is our derivative. dy dt, by the same token, is -5 sine t. If I want to find dy dx, I'm going to compute dy dt over dx dt. Canceling sine t, I get -5/2, the slope of the line. Of course, this isn't going to make much sense if sine t is equal to 0. So we should probably indicate that sine t can't be 0, and then we can note the places where that occurs. All right, and so we might explore whether that's the endpoints of the line or somewhere else. For now, I just want to focus on the computation of dy dx. So let's put a more or less random pair of equations up on the board. So let's say that x is equal to, I don't know, 2x squared minus, 2t squared minus 3e to the t. And then y is going to equal t natural log of t. And so I have no clue what the graph of this looks like, but I want to find a formula for dy dx. And so that's going to be dy dt divided by dx dt. So dy dt requires product rule, and therefore on top we're going to have natural log of t plus t times the derivative of natural log of t. So natural log of t plus 1. Let's check that again. If I differentiate the t, I have a 1 times the natural log of t. If I differentiate natural log of t, but leave the t alone, I have t times 1 over t, which ought to be 1. In the denominator, dx dt, I'm going to use power rule and an easy exponential. And so here is my formula for dy dx. Notice it's in terms of t. So if I want to figure out, say, the slope of a tangent line at a particular x and y coordinate, in particular, I need to know the t value that corresponds to that xy point. So for example, if I were to plug in, I don't know, t equal 1, then I would have x of 1 equal to 2 minus 3e, and y of 1, using this equation, is going to be 1 times 0, or 0. And so I know that this curve, whatever crazy shape it takes, is going to pass through the point 2 minus 3e, 0. What if I'm looking for the equation of the tangent line at that point? Well, we know point slope form, and so we could take y minus the y value, and then we could use our slope from the derivative and times x minus the x value. As usual, we need to remember that the slope is not going to be a big crazy algebraic formula. It's going to be a numerical value. And so what I need to figure out is the value of dy dx whenever t is equal to 1, because that is the t value that corresponds to my xy point. So what happens when I plug in a 1 into this formula? Natural log of 1 is 0, and then I have 4 minus 3e on the bottom. So now we can say that the equation of the tangent line at t equal 1 is going to be given by y minus 0 equal our slope times x minus the x value 2 minus 3e. So this is our equation of our tangent line. And once we have the ability to find dy dx at any t value, we have the ability to answer questions about increasing and decreasing. We can do optimization problems. But the key thing to remember for dy dx is from chain rule, we can use dy dt over dx dt. You're also free to use the prime notation, x prime and y prime. So let's do another quick example using that notation. Find the points where the tangent line is horizontal. Find the points where the tangent line is horizontal, given the following equations. X equals 3 cosine t, and y equals -5 sine t. You might correctly guess that this is going to somehow relate to circles or ellipses or something like that. And so it might be easy, based on familiarity with those parametric equations, to pick out those horizontal tangent lines and their locations. But let's do it using the techniques we just talked about. So first of all, I want to know where dy dx is equal to 0, because I want to know where the tangent line is horizontal. In order to do that, I'm going to compute dy dt, and now I'm going to use this other notation that some of you prefer, y prime of t over x prime of t. And so y prime of t is -5 cosine t, and x prime of t is going to be -3 sine t. And so we can write cotangent, or maybe I'll just leave this as cosine over sine. So 5/3 times cosine t over sine t. Now if I want dy dx to be equal to 0, I need that numerator to be 0. So dy dx is equal to 0 when cosine t is equal to 0 because that's the numerator of that fraction. And we know that if cosine 0, sine is not 0 by our Pythagorean identity. Cosine squared plus sine squared is 1. Cosine, whenever it's 0, will give us sine equal to plus or minus 1. So where is cosine t equal to 0? Well, that's precisely at pi over 2 and any shift of pi from that. So t equals pi over 2 plus k pi, where k is any integer. So if I have pi over 2, or I have pi over 2 plus a pi, which gives us a half rotation, or plus 2 pi, which gives us a full rotation, or minus pi, all of those whole numbers and their negatives, when you apply them as a factor of pi, are going to give us a nice shift on the t value that still preserves cosine equal to 0. So what's values of x and y at those locations? Well, if cosine is equal to 0, we know the x value is equal to 0. So x is equal to 3 cosine pi over 2 plus k pi, and that's going to equal 0. Y, of course, is going to be negative 5 times the sine. And sometimes this is 1 and sometimes this is negative 1, and so we're going to get plus or minus 5 from that work. And so when we look at our, and this does turn out to be an ellipse, when we look at our ellipse, we're going to have particular t values, and they're going to correspond to particular x and y values. And so the points that we're looking for are going to be 0, 5, and 0, negative 5. And with this parametric description, we're going to see that ellipse, everything's going to go around it infinitely often, but we're going to cycle back to these two particular points on the top and the bottom where we see that horizontal tangent line. So I hope this helps you understand how to do dy dx, the derivative, the slope of the tangent line, when you're given parametric equations. Next time we're going to look at the second derivative and how to compute that, which is a little bit more challenging.